So now, in our specific example, we're going to have 20 bidders in just one good. Let's say you really like the M&M package, and you do know what is your own valuation for the good, but you don't know anyone else's valuation, the valuation of the others. You do know, however, the distribution from which the other valuation comes. They know they all come from the uniform between 0 and 10. The auctioneer does not know anyone's valuation, but knows that all come from uniform between 0 and 10, and they're all independent. So, people taking statistics right now, for Tier 1 right now. Carlitos has taught you expectation already. He has also taught independence. So we're going to use a little bit that, as he's spoken about uniform distribution. Good. I'm going to review some of the concepts about uniform distribution. People taking statistics right now, I have them really fresh on their minds. People who are taking, who have taken a long time ago, but have some chance to refresh. So, since we're going to have to use a little bit of statistics, I'm going to review these facts from uniform distribution. Is there any question about the framework of first price auction? Just to make it a little bit more clear. So the utility the person is going to get is going to be their own valuation. The utility is a function of the valuation and the bidding they have. So the utility is going to be, if he wins the good, VI minus BI, how much you value the good minus how much you pay if you win, and 0 if you lose. Simon, do you have a question?
Yeah. Are those uniform distribution random?
What do you mean by that?
They are like from 0 to 12, very low or something. They're very random. Not like all of them that pay like more than 5.
I'm going to talk about the uniform distribution. Let's see if I mean. What I mean is like this. I don't know how much you value, but the distribution of values is going to be a uniform. Which means that there are evenly spaced there. There are people who value very low and people who value very high. Random doesn't mean uniform. Okay? But this is one possible distribution of a random variable is to be uniform one. Which means that so many people between 0 and 1 as there are people between 4 and 5. Okay, I think that before drawing you guys into the facts of uniform distribution. I think it's a good time to have a 5-minute break so guys can refresh your mind and we come back to this. It's 5 minutes on the clock.
要钱吗？你等一下，没有带笔。
They're changing all the time. If they're increasing options, you could.
So this show that you delete the objects, right? Like if you refer to using because I don't really see that too much. Many have not everything
Do you see many first class options? Oh yeah. It's like you just tell me how much you want and then how you spend.
I didn't get it. Are you going to take a look?
This crazy is very cool. Yeah, I would say increasing is more common and first price is more common. But they're increasing the second price and first price is more common. But it also
I just need some.
Common means that we all have the same valuation, but we don't know the valuation. For example, common value would be like we all have the same valuation. We just don't know what valuation it is. For example, you might like M&M different than I do. We have independent valuations for M&M. But if this was a bag of money, $4, I probably value $4 the same. That's cool. Like, let's say we're gonna let's let this oil well in the shelf. They're going to feed this oil well. We don't know how much the oil well is worth. It's going to you, but we know that for you and for me they worth the same. It's another kind of option. There's another kind of setting that is different in this English study. I'm not going to talk about this because it's a very but it's a very important private vendors, which means independent valuations, and the other one of which is have common values. It means independence and fiscal. And the value has no place to do with the other perspective. Only through what it is, not through the values. This means independence is what is independent? If you have more questions, just come down there.
Oh, there we go. I need to help from Microsoft.
Oh, you want to get back your home?
No, I've got so many. One another guesses from there? Probably. Yeah, I think a lot of them are all like
Guys, let's get back here.
yes, sir.
Vector 41 classes here now. Let's say you have a uniform valuation between, in this interval, A and B. How does the distribution look like? Yes? It's a constant value, right? That's what makes it a uniform. So for all possible value, you have a constant there. And does anyone know what is the value of this constant? Well, you know this is a PDF. It has to integrate to 1. So the integral between C from A to B has to be equal to 1. Which implies, oh by the way, this is dx. So the value here, if you have this uniform in this interval A and B, this value here is going to be equal to 1 over B minus A. In our example here, A is going to be 0 and B is going to be equal to 10. So this is just going to be equal one-tenth. Actually, I just realized that all my notes this year is 20. Sorry, guys. So this number here is going to be 1 over 20. Yes? Yeah, that's it. Okay, another important value, result of the uniform distribution is this big F of x is going to be equal to x minus a divided by b minus a, which is the probability that the random variable x is more than x in this uniform distribution. In our example, there's going to be a is 0 and b is 20, so this is equal to x divided by 20. So what is the expected value of a uniform between A and B? Anyone? No? It's going to be just exactly the point here in the middle. Right? It's exactly the point in the middle of the interval. And this point can be given by b plus a divided by 2. All of these, you probably have learned some point in statistics, or at least to get them. There's another result that's a little bit more complicated, and perhaps it's new for you guys. So that's why I'm going to put it in here. And it's a proposition, and it's very useful for solving these specific problems. So this is called higher order statistics of a uniform distribution. It is like this. Let's say I'd like to, yes. Cave. So let's say the first, I would like to, let's say we have 20 draws of this normal 0 and 10. What is the expected highest of this, I said 20, of this 20 draw, oh scheiße, of these 20 draws of the normal 0 and 20? What is the expected highest of them all? An example. So, this is 0 and 21. So all I have to do here is multiply by 20. I'm looking for the k, but now here k highest. K is just equal to 1. So n here is equal to 20 plus 1 minus 1, so it's times 20. Divided by n plus 1 by 21.
How do you know k is 1?
Because it's the highest. The kf high, the kf highest. If I'm looking for the highest, is the first highest. K is just 9.
the K was the second highest, it was the second highest in this case too?
Yes. The 10th highest, K equals 10.
Okay.
Okay?
Okay.
So this would be what we expect to be the highest out of 20 independent draws of a normal 0 and 20.
I don't know why n is 20.
Because I said that n equals 20 of 20 draws. 20 draws and 20 people. Yes. But A is 0. No, it's a good point. Like there are many things here. Here, 0 and 20. This is A. And this is 20. This is opposite. This is B. Okay. So I apply this formula to the above here. Okay. It's a very useful formula, especially for this problem. Okay. Now let's go back to the first price auction. Just another example. If I want to figure out what is the 9th highest out of 20, what number I would get? Okay. What is the expected? I was expecting 90th highest value of the uniform 2, 12. Well, now B minus A, this is A, and this is B. So this is going to be equal 10 times out of 20 draws, right? Plus 1 minus 9 divided by 21 plus, okay, whatever this becomes. Okay, this is just how to calculate higher order statistics of uniform distribution. Yes, I do.
I understood the rule, but I don't understand why do you use it, or what does it illustrate like in English? You want to explain it?
This helps us. I'm going to show you how this is useful in a bit, just very soon. It tells you what is the if I would like to know what is the expected third highest value out of 20 distribution of a uniform, I have a rule of thumb that gives me the value very quickly. Otherwise, you have to solve for multiple integrals. If this is not a uniform, it's a multiple integral problem. So it's a shortcut to solve for this problem.
I mean, what do you mean by expected highest of 20 rows?
Well, let's say we all here have evaluation. How many people we have here in this room? I don't know. We have 60 people in the room, right? We all have evaluations for the M&M. Let's say we have 50, it's between 0 and 5 and 60 people. And I would like to have I would like to know what is my expected second highest value for the M&M. I'll just apply the rule, and you're going to give him a value. Okay? It's a shortcut. Otherwise, you have to solve for multiple integrals. It's more complicated. Any questions? Okay, so now let's try to solve for the bidding function in the first price auction. So we would like to find a bidding function B that maximizes my expected utility for if I bid BI as a function of my own valuation. So, did I erase? So this is my utility. This is a utility that I get if I win the auction, and this is a utility that I get if I lose the auction. Can you anyone tell me what is my expected utility then? Could be in terms of the probability of winning the auction. Look. If I win, I get VI minus BI. If I don't win, I get 0. So my expected utility is going to be my utility if I win minus what I pay times the probability of win Right. I have this utility here, my valuation minus how much I have to pay. If in the case that I win bidding BI, and I get 0 otherwise, so my expected utility is just this times this. Obviously, my probability of winning increases with BI, so this is still an increasing function of BI. I still don't know exactly what it is, but it should be something that looks like this. So I still don't know what it is, but I can take for sure conditions of this, and I can find. So BI has two effects. If I increase my bid as a function of my valuation, I'm going to have to pay more if I win, so it reduces my utility in the case that I win, but also increase the probability that I win. So I have this dichotomy between paying more and winning, or not paying as much and not winning. Yes, I did.
Do I want to maximize my utility or beyond? Utility or beyond?
Okay.
BI.
You want to maximize the expected utility. You're going to choose BI. You choose your bidding that maximize your expected utility. Okay? There's some complicated math washed underneath the roof here now, because you're maximizing a function, this functional calculus, but let's accept that. Any other questions? So if I differentiate this guy here with respect to bi, first order condition implies that pi minus bi times well, differentiating here this function with respect to bi, I get what I win in the case that I win, my utility times the derivative of the probability of winning minus the probability of winning has to be equal to 0. Just differentiate this function here. This is some function. Okay, so it's kind of complicated to solve for this problem here so far, because we have no idea what is the probability of winning given bi. This is actually a differential equation. And it's beyond the scope of this class to solve this problem more generally. So I'm going to make here a very simplified assumption that is going to say that actually what we did, let's make the assumption
That is 2 and alpha.
I'm sorry?
What is that? 2? Alpha?
That's an alpha, yes. Oh, here we go again to the point. And then my alpha is only 2. I don't understand the 2. So let's say my alpha is equal to 3/4. It means that if I value the good 20, I'm going to bid 15. If I solve for alpha be equal to 1/2, it means that if I value the good 18, I'm going to bid 9. So the alpha is going to completely characterize my bidding function there. Could be any number we're going to solve for alpha.
It's not a function.
I'm sorry, say again?
It's not below 0.
Well, in equilibrium, it's not going
I
to
mean,
be.
1.
It's not necessarily 1. I'm not saying anything about alpha. The only assumption so far is there is a linear function like this. It could be something more complicated. It could be x squared or alpha bi cubed, for example. The assumption that it's a linear function, and the problem now becomes to solve for alpha. Okay? So all I'm going to do now is solve for this alpha here, which tells me how much to bid for every possible valuation that I have. Yes.
Sorry, are we given the V and the VI in this
No.
problem?
When
Like, if this was on the exam, are we given the V and VI?
no.
And how is it just to solve for alpha?
The solution is a function.
Oh,
Okay? I want you to solve for VI as a function of VI. It's not a number. Because for every possible bidder, you're going to know your own value. So I would like to have a bidding function. For the auctioneering, the solution is a number. Because the auctioneering does not know. We're going to get to the problem of the auctioneering. Okay? I think that was a good clarifying question because I heard some all were happy with that. So we have to solve for this alpha. We'd like to compute our bidding function. So now let's see what is the probability of winning this auction. So the probability that I win the auction here. Do you agree with this here? You seem to be puzzled. The probability that I win the auction if my bidding is higher than everyone else's bidding. So I win the auction if BI is bigger than B1, which is bigger than B2, that is bigger than B3, is bigger than everyone until B20. It's equal to one of these. How many inequalities are here? How many inequalities are here? 19. Because BI is one of the guys. Yeah, but I just have to be bigger than everyone else but me. I'm sorry, what did you say?
There's 20 with the.
Yeah, one of them is me. So in order to win the auction, I have to be bigger than the other 19.
When you look at the last one, should be 19 or 20?
I didn't say that I equals to 20. Just a notation issue, right? Okay, fine. If I would like to be more precise, I'd like to do something like this. Everyone until BI minus BI is bigger than BI minus 1. BI is bigger than BI plus 1. BI is bigger than B20. Okay, so there's some notation there. I was in the middle. I didn't want to. Right there. Whatever. This is more precise. Yes.
I'm a bit confused now. You said that the problem becomes the source by alpha, so put that aside and you just got back to probability of winning the auction.
No, now I'm going to use the assumption. Now I'm going to use the alpha now. So now we assume that there being an alpha, a linear function of their own valuation. So this means this is equal to the probability that alpha VI is bigger than alpha V1, then alpha VI is bigger than alpha V2. And now if you guys excuse me here, I'm going to go all the way to alpha VI be bigger than alpha V20. Here,
What is that?
are you,
Alpha.
Rohan?
Yeah.
Oh, it's greater than sign. Never mind. I got you.
Is this the question?
Yeah.
Okay.
I thought it was another letter.
Any other question?
I don't know.
Yes.
So you're using the alpha that first one C from fitting alpha range.
Say it again?
There's not different alphas for different
No,
ranges.
there's no different alphas. We all have the same alpha. Because in the end, alpha is just a function of every possible valuation that I might have. So if you have a different valuation than I do, you have the same alpha. Your bidding is going to be different, but the function is still the same. Because we are identical, but by the way that we value the goods different. So different people with different valuations have the same alpha. They have different valuations, they have different bids, but they have the same alpha. And now we can cancel alphas all over here. Alpha, 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 alpha. Right? Because if alpha V1 is bigger than alpha V2, if you don't leave, alpha is bigger than V1 and V1 is bigger than V2. Yeah, we're assuming already alpha has to be positive. But it has to be, otherwise it makes no sense. Like if I have a valuation of 10, I'm going to bid minus 10. It doesn't make any sense. But yeah, I should have written here somewhere. Positive. Otherwise this one just like okay, and now what do we do with this? Which assumption I haven't used here so far? Do you have something to say? How do I cope with this guy here now? What I haven't used so far that we have in the model there's nowhere here in the board, but there's the fact that they are independent from each other. And if those valuations are independent, they are the?
You just add them?
Nope, they're the product of the
Well,
product.
yeah, multiply, yeah.
If A and B, if A is independent than B, the probability of A
And,
to B is probability of A times probability of B.
yeah. Okay. Because this is a uniform distribution, this is because they are the probability that VI is bigger than V1
this happens 19 times here. It's just this number elevated to 19. So now we just have to calculate this number here. The probability that if I am here, if I have my own value vi given, what is the probability that the other guy is smaller than me? Has a smaller valuation than I have. Using the conditional distribution function of a uniform, the CDF, the cumulative distribution function of the uniform, we know that this probability here so this whole number here so this whole probability is just pi divided by 20 elevated to 19. But we would like to have this as a function of bi, because it doesn't make any sense so far, because it's a function of bi, and we are using here vi. But we know that by assumption, okay, so I'm going to plug this here, in this solution here. And this implies, well, not by 2, or by alpha. See? Good. Yes.
How did we get from BI greater than B1 power?
I'm kind of lost. Well,
Yeah, I just went to the next one. How did you get from this to
what is the CDF function of a uniform 0, 20? It's right here. Of a uniform 0, 20, A is 0 and B is 20. So the probability that there's this random variable x